name is Zineb. I prepare my thesis in the National Institute of Post and Telecommunication in Rabat, Morocco. And today I'll be presenting my work on the energy efficiency of IEEE 802.11ax high-density wireless local area networks. So the outline of my presentation is as follows. I will start with an overview about Wi-Fi, then some information about the 802.11ax standard, followed by our analysis of the energy efficiency, a summary of the results we got, and then perspectives. The 802.11 standards are commonly known to the public as Wi-Fi. Are you able to hear me?
Yes, we can hear you.
Okay, so the 802.11 standards are commonly known to the public as Wi-Fi. It's a market worth trillions of dollars worldwide, with billions of users worldwide and billions of devices. And these numbers are getting higher and higher every day. So our focus is on the 802.11 standards, which started in the late 90s. The first, the second, and the third generation were able to reach data rates up to 54 megabits by 2003. The fourth and the fifth generation allowed the users to reach the gigabits for the first time in the form of the standard AC. Currently, the standard 802.11ax is representing the 6th generation and 6E, and it promises even more data rates and higher efficiency for the users. The 802.11 groups are standardizing a next and upcoming 802.11be, which is the 7th generation of Wi-Fi, which is promising data rates up to 30 gigabits. So the shift toward AX happened because there is a departure from the focus on the throughput toward capacity and efficiency for the users. Every user needs more multi-user MIMO options, a higher modulation and coding scheme, and more streams to satisfy several possibilities for transmission and reception and newer scenarios such as the Internet of Things and artificial intelligence. This introduced the high-efficiency wireless local area networks 802.11ax. So as we said, the high-efficiency wireless local area networks 802.11ax is created to provide the services such as dealing with heavy loads access points, more users, and overlapping basic service sets. It also must combat hidden nodes, exposed nodes, and collisions problems, while handling offload data from wired network, outdoors and hotspots, congestion, and high bandwidth applications. The 802.11ax promises a power efficiency, spatial reuse, temporal occupancy, and a better overhead and resource allocation while coexisting with legacy devices and future technologies. The 802.11ax it creates an environment of Mach and energy and spectrum efficiency by options such as a new modulation and coding schemes, the use of orthogonal frequency division multiple access, the use of multiple resource units, the target wake time power saving technique, an extended guard interval and a longer symbol duration to combat interferences, and the use of two-unit allocation vectors to determine frames from the same network and frames from neighboring networks. So in our work, we chose to model a network by the Markov chain with a slotted time scale and a bidimensional process of the backup stage and the backup counter. We represent the transition probabilities as the states the station can occupy and deduce the chain stationary distributions. This allows us to calculate the transmission probability, the collision probability, and the throughput of the system comprised of an access points and several stations. Implementing the new and improves time duration and frame format of the 802.11ax allows us to express the probability of success and the expression of the energy of the system, which finally allows us to deduce the energy efficiency expression. So in our simulation, we started by representing the energy efficiency against a number of stations for different channel widths for the 802.11ax. We notice that the energy efficiency drops as the number of stations increases, which is natural for every type of network. But for the lower channels, the energy efficiency drop is not as drastic as the high channels. This is due to the fact that 802.11ax offers an extensive use of the 20 primary megahertz channel, and which is a power-saving technique. For the modulation and coding schemes, we notice that the energy efficiency for the higher modulation and coding schemes is remarkably better than that of a lower modulation and coding schemes. This is due to the fact that 802.11ax uses very high physical layer data rates, better suited for transmission with more high modulation and coding schemes. Finally, we represent the energy efficiency compared to the contention window value. We notice that as the contention window value increases, the energy efficiency increases, and past a certain point, it starts to drop. This is due to the fact that the contention window allows for a backup time efficient for transmission without interferences. But as the contention window increases, the backup time increases, which creates a longer period wait between transmissions, which uses a lot of energy, and therefore the energy efficiency drops. So in our work, we deduce that finding the best contention window value is for better backup and less collisions and more throughput is the best way to enhance the energy efficiency. And the model which taken into consideration the contention window value is the best joint optimization between the throughput and the energy efficiency. As some perspectives, we propose that the study of the 802.11ac, the 802.11ax, and the 802.11ba is a very interesting fact due to the multi-user operation and the new techniques provided by each node, which provides a novel approach to networking in a world filled with artificial intelligence and Internet of Things networks. Thank you for your attention. And if you have any questions,